Hi everyone, I'm Patricia. I'm a reservoir engineer at Petrobras and a PhD student at Heriot-Watt University. My PhD project studies water management optimization in carbonate reservoirs under CO2 WAG-UR. My supervisors are Professor Eric Mackay and Professor Ken Sorby. WAG injection has been applied in Brazilian carbonate reservoirs due to its potential to control CO2 emissions by reinjecting the produced CO2. These reservoirs are primarily composed of calcite and dolomite, but the presence of other minerals can influence geochemical reactions and change brine composition. In this study, we show that the CO2 concentration in the original oil composition can also significantly affect mineral reactions, despite the large volume of CO2 injected during CO2 WAG-UR. This research investigates the geochemical impact of reservoir properties on brine composition in carbonate reservoirs. The main goal is to improve the prediction of produced brine composition based on reservoir properties, which enables the development of effective reservoir management strategies from the early stages of an oil field project. This analysis uses reservoir flow simulation coupled with geochemical modeling. The software used is GEM from the CMG group with the Wallery database. The model simulates a producer-injector well pair with light oil in a 3D reservoir sector. The rock is divided into 20 grid blocks in each direction. The distance between the wells is approximately 1,400 meters. Simulations start with no injection or production to guarantee that the system is initially equilibrated. Then, low sulfate seawater and pure CO2 are alternately injected. The reservoir zone is primarily formed by calcite and dolomite, with sulfate minerals in smaller amounts. The reservoir temperature is 90 degrees, but the model is a non-isothermal model, so the temperature near the injector block is approximately 40 degrees. The activity model is B dot, the equation of state Spang-Hobson, and his law calculates the CO2 concentration in brine. And the model is kinetic, but the system reaches equilibrium during residence time. Two scenarios are studied with two different oil compositions. The models consider the essential reactions related to CO2 speciation in water and the mineral equilibrium reactions. In each model, the formation water composition is initially equilibrated with the rock and the oil phase. The total amount of light components in the initial oil composition is fixed at 21%, while the heavy components are kept constant. The graph shows the mineral behavior by water per volume injected near the injector well for the 1% and 18% CO2 reservoirs. The low sulfate injected seawater is undersaturated with respect to all minerals, but only calcite and anhydrite dissolve continuously due to their higher solubility. Calcite solubility is strongly controlled by CO2 concentration, while anhydrite solubility is less sensitive to CO2 and more dependent on temperature. Anhydrite competes with calcite for dissolution, and the tendency for calcite dissolution increases when larger amounts of CO2 are present in the oil phase. Dolomite is less soluble than calcite and anhydrite at reservoir conditions and tends to precipitate due to calcite dissolution. Due to calcite and anhydrite dissolution near the injector block, the brine becomes enriched in calcium and sulfate ions. As the waterfront moves away from the injector well, anhydrite precipitates until the system reaches equilibrium deep in the reservoir. The graph shows a grid block 300 meters from the injector well, where it's possible to observe anhydrite precipitation. Nevertheless, the 1% CO2 case shows a lower tendency for anhydride precipitation compared to the 18% CO2 case, highlighting the stronger precipitation tendency in the system more saturated with carbonate ions as a result of the higher CO2 content. When comparing the formation water, injected water, and produced water compositions for both scenarios, a clear difference is observed. In the 18% CO2 case, the sulfate content of the produced brine is reduced due to anhydride reprecipitation deep in the reservoir. In contrast, in the 1% CO2 case, the sulfate concentration of the injected low-sulfate seawater becomes enriched after flooding, even exceeding the formation water concentration. This indicates that low-sulfate seawater can be enriched in sulfate after flooding when the CO2 content in the initial oil phase is low and when there is anhydride in the mineralogy. We can also conclude that CO2 partitioning from the oil in the water phase strongly influences mineral reactions, since the amount of CO2 in the oil phase significantly affects brine composition despite the large volume of CO2 injected during CO2 Wagyu war. I'd like to thank you all for your attention, CMG for providing software licenses, Petrobras for sponsoring my project, Heriot-Watt University, the FAST Group sponsors, and Energy Simulation for the opportunity to present my study. Thank you.